Imagine you roll a dice. What are the chances it lands on a 6? Well, I think this is kind of an intuitive question. I mean, you have a 6, and if we unravel the die, we have these 6 different options. So we can sort them into these 6 possibilities, and we're saying the probability of getting a 6, and there's one 6. So we can kind of start formally saying something like probability of rolling a 6 is 1, which is the correct outcome, and the 6 possibilities. So probability is 1/6. Even more formally, we can replace probability with a p. And so that's all well and simple. But if we move on now to maybe rolling 2 die, this suddenly is a bit more tricky. I mean, what are the chances we roll a 6 with 2 dice? So you have 2 dice, the more dice to get a 6. And it's not immediately apparent. And maybe it is, but it's definitely not as simple as just with one die. But what we can do is the same thing. We have the 6 different faces of a die. We can separate them out into all the different combinations, and we get that there's 36 total combinations of rolling 2 die. We can then go over and count all the different 6s, and we see here we have 11 combinations with the 6. And so it's the same as just with one die. We take all the probability of rolling 2 die, the probability of rolling a 6 with 2 die is 11 over 36, as we have 11 combinations with a 6 and 36 total. Again, we can kind of make this a bit more formalized by saying p of rolling 6 with 2 die, but that was fairly simple again. But let's move on to 3 die, and I think this is where we start realizing that our strategy might be a bit flawed. We can ask what are the chances we roll a 6 with 3 die, and yeah, we can kind of go back to what we did with 2 die, and it's again what we start to realize though is as we go to 3 die, we have many more combinations, and in this case we have 216 total combinations. And okay, so well, sure, why don't we just do what we did last time? We find all the 6s, count them up, and in this case we have 91. When we get, well, okay, so same as last time, 91 over 216, but what we realize is for 3 die, 216 is the total combinations. But as we go up and up, this number gets really big. And so I think we have to kind of redesign how we might want to solve this if we use more die. And so let's think of a simpler way to do this. We start by just thinking of, well, the first roll, are we going to get a 6 or are we not going to get a 6? And we can assign probabilities to each of these cases. For getting a 6, we have that there's 1/6 chance, and again, for not getting a 6, it's the opposite, 5 out of 6, which gives us a total probability of 1. But then we can add on the next event. So we have we're rolling 2 die now. And so you can see that there's, at the top, you have 2 6s, and at the bottom, you get no 6s. And we can build this tree out into the 3 different rolls for our example. And how does this help us? So we've constructed this tree, and what I'm arguing is that this tree can represent those 216 cases. And this is called a tree diagram. And so we're going to use this tree diagram to find out if we get 91 combinations out of the 216. And how we can do this is compute it by getting the first to get 3 6s is 1/6 times 1/6 times 1/6. This is to get 6 3 times in a row is 1/6 3 times. And then to get 2 6s, we can do 1/6 times 1/6 times 5/6. And the 5/6 is the chance that you're not getting it. And so we build out these probabilities, again, for just getting 1/6, and we can start constructing our probability here for rolling 6 with 3 die by first getting the chance that we get all sixes, then adding the chance that we get 2 6s, which we'll have to multiply by 3 because there's 3 different cases of that. And the last one here, the chance of getting 1 6, and again we have to multiply that by 3. And what we'll find is if we compute these numbers, we get 91 cases. So this is good. We've represented the problem in, you could argue, a simpler way, but I'm not quite satisfied with this. This seems not totally simplified. I think it's still a bit complicated. And that's where this formula comes in. And so this is kind of a scary formula at first, but we'll see that it really isn't too difficult. What this formula is called is the binomial distribution. And what it models is cases where you have successful events. And in our case, a successful event is a 6. These letters here are represented as follows: N for total trials, P for probability of a successful trial, and K for successful trials. So we'll go one by one, starting with N. And how are we going to decide what these variables are? So for N, in our case, it will be 3, as that is the number of rolls that we are looking for to get our 91 combinations of 6 for 91 combinations that have a 6 in it. And how the intuitive way to think about why this number is 3 is you have the first roll, and in our branch you can see that that's roll 1, and then you have the second roll and the third roll. So this is the number of rolls for our case. P can be represented as probability of successful trial, and in our first question we noted that this is 1/6, so we have probability of 1/6. And for successful trials, this is maybe the most difficult one in our case to wrap our head around, but I think we can make sense of it here. So for K, we're going to have K is equal to 1, 2, or 3. And the reason for this is 3 is if we have 3 6s, but we also have to consider the cases of 2 6s and 1 6, as these are all cases where they have a 6. But computationally, there's a trick here that we can do. If we note that we have all the cases with 1, all the cases with 2, and all the cases with 3, we can do something smart here where we take all of these cases and we also think of the cases where we don't have a 6, and we can take this and understand that the green area here is when we have greater than 1/6. And what that big X is saying is a random variable. And these are the cases where we have more than 1. And in the red area, this is where we don't have any 6s. So X in this case represents how many 6s we have. And we can do some fun math here, which is a very basic example, but it's just saying that the probability of getting greater or equal to 1/6 is just the total probability, so 1 minus the cases that we don't get a 6. This is called the complement rule, and you see this a lot in probability where sometimes it's easier to get one case than the other. And so what we can do here is change our question into K equals to 0, as that's a simpler method, or it's simpler to compute. And then once we have our answer, we can just do 1 minus this answer. So now we have all the variables that we need to make this computation, and it's as simple as just putting the variables in. And we, again, here at the very end, see that we have 91 combinations out of 216. And so that was a lot, but essentially it just, if we know a few variables about our situation, we can see that we can get to our answer without counting all those 216 different cases. And where binomial distribution really takes effect is, when you get larger numbers. So let's for example imagine you're rolling many die. This could be up to 1,000, even more. So what we can do is, let's say for 100 die, we just change our n variable here to 100, and we do the same computation as we did before, and we get our answer. There's no counting here, as counting 100 die would be 100 or 6 to 100, which is, I mean, a number bigger than anyone is ever willing to count. And so the main idea to grab from this is it's really, if you can kind of start to understand the problem, then you can make these simplified expressions like the binomial distribution, which can make your computation much easier. And all that's required is understanding the problem a little bit. And so this is probability. It's kind of, in essence, we can, if we can simplify problems, then we can find answers much quicker. Thank you.